Okay, welcome to part 10 of Laplace transforms. It is connected with the very special operation convolution. This shun, many shuns, for example, addition, okay, subtraction, multiplication. So also one more shun, that is composition, okay, composition of functions. Now we are coming to one more special operation, that is called as convolution. What is this convolution basically? First let us understand that one. For example, if I have two functions f of t and g of t, by taking the product f of u, I will just change the name of the variable, and g with the input t minus u. If I integrate this with respect to u, okay, and the limits are from 0 to t for u, if the integration is performed with respect to the variable u and the limits are substituted as 0 and t as lower and upper limits in place of u, this complete becomes as a function of t, because u will be gone and t will appear in place of u, and hence it's not f, for example, okay, sorry, it is some h of t. This h of t is called as the convolution of this f and g. In short, we say this h of t is f of t star. It is not circular dot or plus or minus, it is star here, f of t star g of t. Now let us do the convolution operation with some simple functions. Okay, you can take the screenshot if you want it. Okay, for example, I say find e power t star or e power 2t star e power 3t. Okay, so I am not multiplying this two, I am not adding this two, I am not finding the composition of this two, I am finding the convolution of this two. So how do we do that? F of t star g of t, it should be there in your mind that this product should come as a function of t. So the other variable which is used is named as u. We can name it as any other variable, v, w, anything. So u equal to 0 to t, f of u, okay, that first function is relabeled with u, and g is relabeled with t minus u. Variable of integration is u, limits are in t, so finally function comes in terms of t. Implies e power 2t star e power 3t is equal to, what comes now? Integral u is equal to 0 to t e to the power of 2u. The first function we are making t as u, in the second function t as t minus u. So e to the power of 3 times of t minus u du. Now just now if you look at this, it is integrated with respect to u, so t is silent in that case. It is constant in that case. So e to the power of 3t has nothing to do here, it will come out. E power 3t is out. Now remaining is e power minus 3u. With this e power 2u becomes e to the power of minus u. Now the integration is done from 0 to t with respect to u. Okay, please take the screenshot for this. Now that is equal to e to the power of 3t into e to the power of minus u by minus 1. Limits are from 0 to t. So it will be minus e power 3t out, and the limits are substituted. So e power minus t minus e power 0, that is equal to e power 0 is 1, 1 minus e power, that I am adjusting with this minus. So 1 minus e power minus t into e to the power of 3t. Now on simplification it will be e to the power of 3t minus e to the power of 2t. Okay, therefore e power 2t star e power 3t is e to the power of 3t minus e to the power of 2t. But don't draw any conclusion that convolution is nothing but the difference where the functions are interchanged, not like that. It will be very different sometimes. But one thing is clear, if you work out, you will come to know that f of t star g of t is same as g of t star f of t. But don't keep in mind that f of t star 1 is f of t. Okay, it is not multiplication, it is convolution. You can see that this is not true. Okay, you can take the screenshot for this. Okay, this operation of convolution is helping us a lot in finding the inverse Laplace transform. First of all, let us understand the main core of this chapter, that is solving differential equations using Laplace transforms. The idea is there will be a differential equation and there will be some unknown. Okay. Unknown, for example, y. If I say y double dash minus 2y dash plus 3y is equal to e to the power of 2t, you are becoming clear at this point of time that y is something which is depending on t. So when 3 times of y is added with y double dash minus 2y dash, then that is resulting as e to the power of 2t. What is y which is a function of t? That's how much. Now if the conditions are given that when t is 0, y value is 1, when t is 0, y dash is 2. For example, these two initial conditions are given. Then you know very well that this is a differential equation which has a general solution consisting of two independent solutions because it is a second order. Now, after solving, after getting the general solution using these two conditions, we will get the values of arbitrary constants. That arbitrary constants will substitute back, we will get a particular solution. Instead of going this way, first finding the general solution and then getting the arbitrary constants particular values and then getting the particular solution, the Laplace transform gives us a very elegant way to get the solution of this differential equation using the conditions in the beginning stage, and there is no need of involving the arbitrary constants there. The required particular solution directly comes as a particular solution. There will be no involvement of arbitrary constants or the general solution. Now the procedure here involved is this simple diagram. Okay, now when this y is unknown and the conditions are given, of course, when this y is unknown, what we do is we will apply Laplace to this throughout. So Laplace of this complete is Laplace transform of e power 2t, the right hand side will be 1 by s minus 2. Similarly, some function of s will come. From that, as we have seen in earlier part of the Laplace transform videos, that L of y dash and L of y double dash, they all can be expressed in terms of L of y. So applying the Laplace transform for this, okay, applying Laplace transform, we get the value of L of y as some function of s. We will do a problem on this one. I mean to say only the outline of that. That is, for a differential equation, if we apply Laplace transform, then the y which is unknown, but given a differential equation along with that, it is giving some condition in terms of y and t. So applying the Laplace transform, we will get L of y. When L of y is known to us, y is nothing but L inverse of that f of s. So y will come if we are able to find this inverse Laplace transform. So there are basically only two steps involved. First, applying the Laplace transform, finding that Laplace transform of y, and that unknown y comes if we take the inverse. So if we know how to find the Laplace transform and we know how to find the inverse Laplace transform, we will get back our unknown function y. Now in process, we need the techniques to find the Laplace transforms. For example, if I apply L to this one, then L of y double dash minus 2 times by linearity property, minus 2 times of L of y dash plus 3 times of L of y. L of y is unknown, but L of y double dash can be written in terms of L of y. L of y dash can be written in terms of L of y. So in what way it is related, we need to know the techniques for finding the Laplace transforms. Once we know that, once we do that, we will be ready with the value of L of y. It comes as a function of x. Then we need to know the techniques of finding the inverse Laplace transform. So in previous part, I think part 9, yeah, part 9, I said this is part 10. In part 9 I said how to take the inverse Laplace transforms using partial fractions. Now this convolution operation also provides a very nice way to find the inverse Laplace transform. In what way it helps us? That depends upon the convolution theorem. If you want, you can take the snapshot of this. Now the convolution theorem is like this. Convolution theorem. If L of f of t is f of s, the other way to write this is L inverse of f of s is f of t. Okay, and L of g of t is g of s, the other way is L of g of s is equal to g of t. Then L inverse of this product, okay, f of s into g of s, here it is just ordinary product. If we know the inverses of two functions individually, then the inverse of this product is nothing but just the convolution of these two functions. Okay, so this is what is the convolution theorem. I am planning to upload the proofs of the theorems which I didn't discuss in a separate video, because there may be some students, those who don't want the proof, they want only the application of that. So interested people, however, whether it is available in this part or some other part, they will visit that part. I will mention whatever theorems are discussed in that particular video, I will mention that one. So you can visit that video later on. Right now, let us use this theorem to find the inverse. Now suppose if the question appears, okay, let's do a problem. Example 1. Find L inverse of 1 by s minus 1 into or s minus 2 into s minus 3. Now we have two options for this. Either you split into partial fractions and then separate L inverse. That is one way. You can do that way, and we have done in the earlier class, finding that one. The other way is you can treat it as 1 by s minus 2 into 1 by s minus 3. Then it looks like L inverse of f of s into g of s. Then L inverse of f of s is nothing but f of t. We need to know that. And we need to know what is the individual inverse for 1 by s minus 3. Then that f of t and g of t will do the convolution, as just now we have done the convolution. So let us do the problem in that way. You take the snapshot for this. Okay, fine. Now let's do this one. We know that L inverse of 1 by s minus 2 is equal to e to the power of 2t. That is nothing but some f of t, say. And L inverse of 1 by s minus 3 is equal to e power 3t. That is nothing but some g of t, say. Okay, I did not plan, but luckily it's fine that we are ready with this convolution as just now we have done. Therefore, by convolution theorem, L inverse of this product of 1 by s minus 2 into 1 by s minus 3 is e power 2t star e power 3t. Just now we have done, it is e power 3t minus e power 2t. Now the other way, if you want, of course this is nothing but equal to implies L inverse of 1 by s minus 2 into s minus 3. Okay. Now the other way, if you do it by partial fractions, I think you know the point that there is only one unit difference, so this can be very easily splitted like this. Okay. So this I can write it as 1 by s minus 3 minus 1 by s minus 2, because s minus 2 comes here, s minus 3 comes here. Okay, partial fractions, that is the way, this is the shortcut now. The difference is only one unit. Now s minus 2, s minus of minus of s minus 3, that is minus s plus 3. So 3 minus 2 is 1, so 1 by this one. Now if L inverse of this is L inverse of this, that is nothing but e power 3t, L inverse of this, that is nothing but e power 2t. I hope you are clear about this one. So this is the way convolution theorem helps us in finding the inverse of the product if we know the inverses of the individual functions. Now for example, if I have L inverse of 1 by s square plus 1 into s square plus 4, then what I need to do here, or I take s by, then I can write it as L inverse of 1 by s square plus 1 into s by s square plus 4. Okay, then in this case it can be written as f of s, this one is f of s, this one is g of s. If we know L inverse for this and L inverse for this individually, then by taking the convolution we will get this one. So this is nothing but f of t star g of t, where this f of t is nothing but the inverse transform. So the other way to write convolution theorem is L inverse of f of s into g of s is equal to L inverse of f of s. This is same like writing f of t. So star L inverse of g of s. So what is L inverse for this one? That is nothing but sin t, and this is nothing but cos t with 2t, cos 2t. Now sin t star cos 2t is the convolution of this one. Just I'll write one step. I hope you will be able to finish off this one. That is equal to integral u is equal to 0 to t sin u for this one, t is replaced with u, and the second one cos 2 t is replaced with t minus u, and du. Integration is with respect to u and limits are 0 to t. If you substitute the limits, it should come as a function of t. Now you can do one thing, it is cos 2t minus 2u. So if it is 2 here available, 2 sin a cos b, you can write it as 2 sin a cos b, sin a plus b plus sin a minus b. So you need 2 here, take 1 by 2 and 2, split it as per transformations, then separate the two parts, do the integration, you will get the result for this one. So this is the way how we can find the inverse of a product if we know the inverses for the individual two functions. Find the inverses of individual functions and apply the convolution. I hope you are clear about this. If you want, you should take this screenshot. Okay, in this part of Laplace transforms, which is mainly dealing about the convolution, I would like to make one point clear to you, that you don't get confused with the concept of inverse. If you know any rule of Laplace transforms, it will give you a rule for inverse Laplace transforms. Let me talk about 1 or 2 examples and you will become very clear about it. For example, L of e to the power of at into f of t. What is this one? It is nothing but f of s minus a. If L of this function f of t is f of s. So if the Laplace transform of a function is f of s, then the Laplace transform of that same function f of t multiplied with e power at is just changing the transform. Now let us see how to write the same concept in terms of inverses. This comes this one. So if L inverse of f of s, this one, L inverse of f of s is f of t, then L inverse of f of s minus a is, I am taking that L this side, nothing else. L inverse of f of s minus a is e to the power of at into f of t. I hope you are clear. Now a very important point to be noted, that is, if L of f of t is f of s, then L of t into f of t is equal to f dash of s with minus. Now if we read this concept in inverse transforms, then if L inverse of f of s, this one L inverse of f of s is f of t, then L inverse of f dash s, I should write minus, that minus I am adjusting it to as per linearity property, constant can be taken outside. So minus t into f of t. Now sometimes it happens that we will not be able to calculate L inverse of f of s directly, but if we know what is L inverse of f dash s, then we will be able to tell what is L inverse of f of L inverse of f of s. Simply, if you know L inverse of f dash s, and that is this one, then this f of t is nothing but L inverse of f of s. So you can tell what is L inverse of f of s if we know L inverse of f dash s. In some other video I will tell you how to use this rule to find the inverse Laplace transform, and in the next video we will see how to solve differential equation using Laplace transform. Okay, thank you.